Alright, so we're going to get started with this video. This should be, I think, problem set number 5. And it's got quite a few questions, as you can see, and they each have at least a couple parts, it looks like. But we've got about 14 questions in total. We're just going to start from the top and work our way down like usual. And so this very first question wants us to use the bisection method to figure out about where the root or the zero is for a function that we're going to be determining. So it says right here, use the bisection method to find a number in this interval from 0 to 2 inclusive that approximates the cube root of 4 with an error less than 1/8. So the first step for this one is to define a function in these terms that has this number as a 0. And so I know I'm going to have whatever it is, I'm going to have x to the a minus b is going to equal 0 when x equals the cube root of 4. Right? Because we want to find the 0 when this is our x value. So if we plug that in for our x, then we can see here we want to undo this cube root. So the easiest way to do that is to set a as 3. So it turns pretty quickly into this, which obviously the cube root and the cube cancel out, so it just becomes 4 minus b equals 0. So b has to equal 4. So our function f of x is going to be x cubed minus 4, because we just found that a needs to equal 3 and our b needs to equal 4, so we just plug those back in right here. And there we go. We've got that first step done. I'm going to erase this really quick. The next thing we have to do, it asks us how many steps does it take to get within 1/8 of the solution. So we just came up with a function that has this x value. Oh, that's the eraser. Whoops. That has this x value be the 0 of the function. That's where our root is. And now we want to take this function and use the bisection method to approximate our 0. So the first thing we're going to do, we know our interval is from 0 to 2, and we know that that has a maximum error of 1. And if you're not sure whether it's 1, I really recommend going back and watching my video on intermediate value theorem and bisection method. I'll put that in the description just so that's a quick link, but it is in the same playlist and it was uploaded right before this video was. But so this has a maximum error of 1. And so what we're going to do is we're going to cut that in half, because that's the entirety of the bisection method. We just keep cutting our interval in half until we get within the desired tolerance. In this case, we want to be within 1/8 of the actual 0. So I'm going to plug in a 1 because that's going to be right between my 0 and my 2 on that interval. So then we'll find f of 1 equals 1 cubed minus 4 is a 1 minus 4, or a negative 3. And, well, first of all, we actually need to double check that we can even use this interval for the bisection method, because remember that for the bisection method to work, our interval has to essentially pass the intermediate value theorem, which means that one of our values has to be negative and the other has to be positive for us to, when we plug it into our function, for us to be able to guarantee that there's a 0 in there. So let's plug in just to double check before we get too into it. If I plug in f of 0, that's going to be 0 cubed, which is just 0, minus 4. So f of 0 is a negative 4. So f of 2, in order for this to work, has to be positive, or else we can't actually do this. So let's plug in that 2. We get 2 cubed, which is 8, minus 4 is 4, and there we go. So this is our negative one, and this is our positive one, which works out perfectly. Now, because this is our negative one, and we just found that f of 1 is a negative number, now we're going to change our interval. We're going to plug in that 1 instead of the 0 to replace our negative end of the interval. So now our new interval becomes 1 to 2. And this has a maximum error of 1/2. So now we need to figure out, we need to cut our interval in half again. So what value is right in between 1 and 2? Well, that's going to be 1.5, or I'll use fractions for this, 3/2. So f of 3/2, that's going to be 3/2 times 3/2 times 3/2, because it's going to be that cubed. Which is, I believe that should be 27/8 to start. So it's 27/8, and it's going to be minus 4, which is going to be the same as 32/8. And so, let's see, 32 minus 27. So this is going to be negative 5/8, and I'm just going to erase this actually so we can write that more clearly. So it's going to be negative 5/8. And again, this is not within our desired tolerance yet, because we want to have an error of less than 1/2, or sorry, we need a maximum error of less than 1/8. And right now our maximum error is 1/2. So again, this is our negative number, so we're going to replace that 1 with the x value we used here. So our new interval becomes 3/2 to 2. And these are only 1/2 away, so it's going to have an error of 1/4. Now, this gets a little tricky because of our fractions. So now I need to add 1/4 to this, because that's going to be right in the middle of that. So right in between 3/2 and 2 wholes is going to be, I believe, 7/8. I think that's correct. Yeah, should be 7/8. So we're going to plug that into our function. And so 7/8, cubed, that's a little bit trickier. So I know 8 cubed is 512. 7 cubed, I won't lie, is a little bit out of my mind. That's 49 times 7. That's going to be 343. 343 over 512. And again, we're subtracting 4. So that's going to be, wowza. That's going to be whatever this times 4 is, which that's going to be, it's going to be 20, 48. Good Lord. That's glad we don't have to go much further. Let's see. Don't worry too much about this. I'm just figuring out what that ends up becoming. Okay, so it's going to be negative 1705 over 512. And it doesn't really matter exactly what this value is right now. It just matters that we find out it's negative. So I know that I'm going to put this in place of our x value for our negative. So we're still looking in the interval. And the reason that we want to replace 3/2 instead of the 2 here is because the 3/2 is our negative number, is the one that gets us a negative number when we plug it in. And this also gets us a negative number. If I replace the 2 with this x, then both x values within my interval would result in a negative number, which would mean that we can't guarantee there's a 0 between them. There might be a 0 between them, but we can't guarantee it at that point because it doesn't satisfy the intermediate value theorem. So we're going to plug that in. And now this has a maximum error of 1/8, which means that whatever we plug in next works out. So what we just found is that it takes 1, 2, 3, 4 steps to get within 1/8 of our solution. So that's going to be our answer there. It's going to be 4. And now we just need to figure out what our approximation is. So we're going to plug in whatever is right smack dab between our 7/8 and our 2 wholes, which should be, I think, 15/16. I don't imagine that we wouldn't be allowed to use a calculator for this, so I'm going to go ahead and use a calculator for this. I know on our actual homeworks we're allowed to use a calculator for the bisection method, but I cannot guarantee on any exams, obviously, that we will be, or even that we'll be doing the bisection method, but I would just get familiar with fractions and our decimals so that we're not struggling too much with that one. So if I plug in a 15/16, let's see, we cube that. We get some really large numbers here. All right. Okay. Very fun. Very, very fun. I feel almost like I messed up somewhere just because of how large these values are. Oh, silly, silly. Okay. So I did 7/8 instead of 7/4. So we're going to have to redo this step. My apologies. Let's erase. Oops. Oh, goodness. It won't erase what I actually want it to. Okay. So we have to erase this bit. Why won't it erase? Good Lord. Erase that bit. And instead of 7/8, we need to use 7/4. Sorry. Oh my god, I almost did it again. Let's try that over. So 7/4 cubed. So 7 cubed was this, and then 4 cubed is 64. That makes more sense. And that's going to be 256. There we go. That makes a lot more sense. So that's going to get us 87 over 64, and that's a positive number. So instead of replacing this x value, we're actually going to replace our 2. So that stays a 3/2. This goes up to 7/4. Right, and these are 1/4 away, so we have a maximum error of 1/8. And now, smack dab between them, let's see, that's 6/4 and 7/4, which means that's 12/8 and 14/8. So smack dab in the middle, we want 13/8. Let's go ahead and plug that in and see where that gets us. 13 cubed is rather large. An 8 cubed we said was 512. 512 times 4. And that is going to be a positive 146 divided by 512. And we see that this is obviously going to be pretty close to 0, right? Because we've got a very large number on in our denominator and a relatively much smaller number in our numerator. So it's going to be pretty close to 0. So our approximation is going to be this. It's going to be, let's see, our x is 13/8 and our y is approximately there. That's the approximation of our 0. And let me just do one thing really quick. Let's see, 13/8. And so we can double check that because we know that our 0 is the cube root of 4 because we designed the function to have a 0 at x equals the cube root of 4. So we know our 0 should be the cube root of 4, which I just said a bunch, which is, as a decimal, a big long decimal. It's something like this if you plug it into your calculator. And we can see that we got really, really close with our 13/8 actually, because if I look at that as a decimal, these are really close. They're really, really close x values. So it tells us we did a really good job with our approximation, and we know that we got within our desired tolerance. So that is done. Moving on, we want to do this right here. It says let f of x equal 2x squared plus 5. We want to use this definition to figure out the derivative of f of x when x equals 3. Or we could read this as f prime of 3. So we know that the derivative here is going to be our a is 3. So it's the limit as x approaches 3 of, is going to be f of x minus f of a, and we actually don't want to write that out. We do want to expand that. So it's going to be 2x squared plus 5x minus whatever f of a is. So if we plug in that 3, gets us a 2, 3 squared plus 15 is a 2 times 9 plus 15 is 18 plus 15 is 33 over x minus 3. And then obviously if we were to plug in that 3 now, doesn't work out super great, right? Because we get a 0 in our denominator and probably a 0 in our numerator as well. So we want to see if we can factor anything out to simplify this at all. So I'm just going to write this bit over here. And normally we would continue to write the limit in front of it, but I really just want to focus on the algebra of this, so I'm not going to do that right now. But you generally do want to. So let's see, we know that this is a negative number. So I know that, and this is positive, so I know my larger number is going to be positive, and I'm going to have a small negative. So let's come up with, let's see, this is tricky because our a value here is a 2. I'm not 100% sure that we can factor this, but I do want to give it a go. So let's think about our factors of negative 33. We've got 1 and 33, we've got this, and I think that's it, actually. So, oh, that works out perfectly, actually, because I see that if we do 2 times negative 3, that'll get us a negative 6x. And if we do 11 times x, it gets us obviously 11x, and 11x minus 6x equals 5x. So that gets us where we want to be. And I know that wasn't too great of an explanation on factoring. I'm not very good at explaining my thought process with these, unfortunately. So if you need help with factoring, I suggest looking at other resources. So again, we want the 2x to multiply with that -3, so I'm going to do a plus 11 here, and then an x minus 3 here. And if we were to FOIL that out, right, I see I get a 2x squared from this first bit, and then I do that next bit and I get -6x, and then I go plus 11x minus 33. I combine like terms, and that's exactly what we started with. So we factored that correctly, and I'm gonna rewrite that actually because I just made a mess of it, didn't I? So that's the same thing as this. If we factor that out, and now we've got our x minus 3 is cancel. So now it just turns into a 2x plus 11. So we've simplified that, so I'm going to rewrite it over here now as this. And now we can just plug in that 3, which gets us a 6 plus 11, and our answer is 17. All right, let's move on to number 3, and this one's a little bit trickier. Let's see if I remember how to do it. So they tell us that y equals 19 over x. We want to find dy dx, or the derivative of y in terms of x, where we have some value of a over x to the power of b. And so when we want to find our derivative, again, the derivative of a function, so our dy dx, and they've actually got this bit down here for us. So our dy dx is the limit as t approaches x, and this is the same as, let's see, as this, just about. So don't worry about it too much. It's not actually anything new. We're just doing this. And actually, give me one moment. I want to pull up our textbook just so we can see where they define this really quick. All right. So here we are. Again, this is our derivative is this f prime of a equals the limit as x approaches a of this bit right here. And we can scroll down further and see them redefine it with an f of t instead of an f of x. And it changes nothing. It is the exact same. And here they rewrite it again, where x is the same as our a and t is our original x. So it's f prime of x equals the limit as t approaches x of this quotient here. So now knowing that, right, we want to plug in our f of t, or in this case we've got a y, not actually f, so it's going to be 19 over t minus 19 over x, and then over t minus x. And this is pretty ugly, but I'm going to rewrite that quotient over here so we can work with it algebraically. Again, typically when you're working through the steps to simplify this, you do want to just keep writing the limit part in front of it, but I, for the sake of my wrist, am just going to work with it algebraically like this. So I'm going to focus on this top bit here, and I'm going to see that they do not have a common denominator, and I want them to. I want to combine these two fractions, so I'm going to give them the common denominator of t times x, right? Pretty simple, just multiplying our denominators. So this is going to turn into 19x minus 19t over t times x, right? You see I multiplied this by x, and this by x, and this by t, and this by t, and then I just combined them, right? And that's still over our t minus x. We can't forget that. And now I'm going to factor out this 19 up here. So it turns into an x, 19 times x minus t over t times x, all over t minus x, and we're really, really close to being able to factor something out here, or to being able to cancel those out. But this is an x minus t, and this is a t minus x. So what I want to do here is I'm just going to factor out a negative with my 19. So it's going to be a negative 19 now, because I'm taking a negative out of here, which turns that negative and that positive. So it goes negative 19, right? And then again, still all over t minus x. And now this, because it's addition, we just move them around. So I'm going to bring that down over here. I'm going to say it's equal to negative 19, and it's a negative x plus t, which I can rewrite as t minus x, right? All over this, all over this, right? And I could actually rewrite that a little bit. Instead of using a fraction bar, I can write it like this. Which shows us pretty clearly that this is going to be able to cancel out with this right here, which just gets us a negative 19 over t times x, which if we go back in and plug that in here, right, we've got a negative 19 over t times x. That's going to get us, because t is approaching x, we just plug in x for our t. That gets us a negative 19 over x times x, or a negative 19 over x squared. And I know we skipped the first part of this question, but the trick with that is this is how we just found our answer, right? So we just found the derivative of y. We found dy dx equals negative 19 over x squared. So our a, in this case, is going to be that negative 19, and our b, right, is going to be 2. And if any of that was confusing, I implore you to just rewind, maybe slow down the video a little bit. I know I went through that pretty quick. Whoops, did not mean to do that. And if you're still confused after the fact, once again, Khan Academy and Google are your very best friends. I know they're certainly mine. So let's move on to number 4. And it's the same thing, except now they don't have us do this bit, but we're still going to have to do it to find our derivative in this case. We could use other derivative rules like the power rule and whatnot, but we haven't learned those in class yet, so we're going to stick to using our limits just so that we can really drill those in. So y in this case is 12 over x cubed, and we want to find the derivative of it in these terms and figure out what a and b are going to be. So once again, we set it up. It's the limit. So So dy dx equals the limit as t approaches x of our f of t, right? So it's going to be 12 over t cubed, 12 over t cubed minus f of x, so 12 over x cubed, all over t minus x. And we're going to do the exact same thing that we did in the top one, except now there's some cubes involved, so it gets just a little bit trickier. So again, I'm just going to work with this algebraically. I'm going to do that over here. So 12 over t cubed minus 12 over x cubed, all over t minus x. Once again, I'm going to give these a common denominator by just multiplying them out. So that's going to be 12x cubed minus 12t cubed over, let's see, the common denominator would be t cubed x cubed, and all over, and I'm actually going to write that as division instead of that extra fraction line, just so that we don't get too hung up on it. And again, we're trying to factor out, excuse me, we're trying to factor out this t minus x. And so we're going to bring that down. We're going to factor out, we see that we're going to have to factor out that negative again. So we're going to factor out a negative 12 from the top. Goodness, sorry. And that's going to get me a negative x cubed plus t cubed all over this and divided by that. And we just keep on going. And again, I'm just going to flip those around. And now the trick here is that this is a perfect cube. And if you don't remember the rules for factoring a perfect cube, that's okay. I always forget them too. They're not the easiest to remember. It's just some blatant memorization. But I think that it is something like this. So if I have this, I think I can factor that out like so. I'm gonna have to double check that really quick because I am not confident in that. Give me 1 second to double check. That's just gonna be a cubed plus a squared b plus ab squared, and then minus ba squared minus ab squared minus b cubed. And so those cancel, and then we get a cubed minus b cubed. Oh, good. So this is right. That little rule up there, which means that we can factor this out happily. So this is going to be a negative 12, and then we get our t minus x times t squared plus tx plus x squared over t cubed x cubed divided by t minus x. And now we can cancel these out. And so this just turns into, and I'm actually going to write it up over here. So it just turns into a negative 12, this long thing here, and oops, don't forget our cubes. And now, remember we want to put that limit back in front of it, so it's the limit as t approaches x of this, and so we just plug in our x wherever there's a t and combine like terms. So that's going to get us, oops, nope, because we're plugging it in. So it's going to be a negative 12 x squared plus x times x plus x squared over x cubed times x cubed, which is going to be negative 12, and this is going to be an x squared, so we've got negative 12 times 3x squared times x to the 6th. And obviously those cancel a little, so we actually get, let's see, negative 12 times 3 is negative 36, and that cancels out and turns that into a 4 because of our exponent rules. And so this is our answer. So we just got that dy dx here equals negative 36 over x to the 4th. So in this case, our a value is negative 36, and our b value is 4. All right, on to number 5, which is another problem just like that. We're doing the exact same thing still. So again, and I'm actually going to write it over here this time. So dy dx is going to equal the limit as t approaches x of, in this case, our y is not a quotient, which actually makes it a little easier on us. So it's going to be 9 t squared minus 4 minus 9x squared minus 4, which turns it into a plus 4, and then over t minus x We'll keep going. So it's the limit as t approaches x. Obviously our -4 and our +4 cancel out. So we've just got 9t squared minus 9x squared over t minus x. And once again, we just want to cancel out that t minus x. And it looks like we've got ourselves a perfect square. So let me just we want to factor out that 9 first. Now I've just got t squared minus x squared. And then we come down here and we keep on going. That's a 9. And since this is a perfect difference of squares, if I can factor it like so, feel free to double check that. Now these cancel. We've just got the limit as t approaches x of 9 times t plus x. If we plug in that x, it's going to be a 9 times x plus x, or a 2x, which means we get 18x. Oh, whoops. So dy dx in this case equals 18x, and we notice there's a plus c. In that case, our c is 0. So c is 0. We get 18 is our a, and this is going to be an x to the first power. And that's all that is. So now we just want to find the value of this derivative at x equals -3, which is just plugging in a -3 for x after taking the derivative like we just did. So it's going to be an 18 times -3, which is a -30 plus -24, and I believe that should be -54. All right. Number 6 now is a little different because we've got this function h of x equals the absolute value of x plus 4. And we want to figure out whether or not this function has a derivative at x equals -4. Well, we can first figure out, we can look for the limit as x approaches -4 of the absolute value of x plus 4 minus plugging in that -4, right? Because that's our f of a, which just gets us a 0 all over x minus -4, so x plus 4. All right, so that's the absolute value of x plus 4 over x plus 4. We can't plug in that -4 there, and if we were to graph that, we kind of see that there is no derivative there because of this hole. This is non-differentiable at this point, which means that h prime of -4, or the derivative of h at -4, does not exist. Number 7 now, we're given f of x equals the cube root of x, and we want to find the slope of this function at the given point, which is 8, 2, and come up with the slope-intercept equation of the tangent line at that point. So remember, we find our slope by plugging it in. So our definition in this case, our x value at the point given is 8. So as x approaches 8, we get cube root of x minus the cube root of 8, which is 2 over x minus 8. And let's see what we can do there. So I do want to simplify that, and that's a pretty tricky one to simplify, but I think that this is just part of, say, a perfect cube of that. So let's try factoring this as though it were a perfect cube. So we'll get this up here, and then the cube root of 3, or not of 3, sorry, the cube root of x. Remember, our perfect cube is if we have this, we can factor it out like so. So we get the cube root of x, right? Minus 2, which is already, we can see that cancels, but let's finish factoring first. It's going to be the cube root of x squared, which this is pretty ugly, I know, which is 2 times the cube root of x plus 4, because it's a cube root of 8 squared. And then these cancel out, and we're just left with, obviously that's a 1 over this bit here. So we'll plug that in over here. So it says x approaches 8. That's going to be cube root squared plus 2 times, oh, that should be the cube root. 2 times the cube root of x plus 4. And if we plug in our 8 for that, so it's going to be, let's see, the cube root of 8 is 2, 2 squared, that should be a 4. Plug it in there, that should still be cube root. Cube root of 8 is 2 times 2 is also 4 plus 4 is going to be 12. So we just found that our slope at the given point is 12. So now we know that y equals 12x plus b, but we still need to find our y-intercept, right? Because this is slope-intercept form. So they gave us the points. We're just going to plug in those values. We know that it's 2 equals 12 times 8 plus b, and that's going to be 2 equals, I believe that should be 96 plus b. So b equals negative 92, which means that our equation is going to be y equals 12x minus 92. All right. Now for number 8. Oh, whoops. Okay. So number 8 also has a couple of parts. It says, say a particle is moving in such a way that its position is given by the function s of t equals 9t squared, where t is in seconds. We want to find the velocity of the particle at t equals 1/3. So the good thing to know is that the velocity of a function, oops, sorry, not the right thing. The velocity of a function is the same as the derivative of its position. So what we want to find is the derivative of the position as t approaches 1/3. So in this case, it's going to be t approaches 1/3. And again, we set up our derivative, so it's going to be s of t, so it's a 9t squared, minus s of 1/3, which I believe 1/3 squared is 1/9, times 9 is 1, then over t minus 1/3. Okay, and now we want to simplify this. So once again, like usual, we're going to be looking for anything in here that we can factor. And I'm just going to factor out that 9 because I think that it might help us. Just kind of a little bit of intuition. Just kind of practice doing these. And right off the bat, I see this is actually a perfect difference of squares. And so if I factor that out, I'm going to get a t, and obviously the square root of 1/9 is 1/3, so it's going to be t minus 1/3 and t plus 1/3 over t minus 1/3. These cancel, we're left with 9 times t plus 1/3, which we plug in to, and actually I'm going to distribute that 9 out. Oops. Why won't it? Okay. I'm going to distribute that 9, so it's going to be 9t plus 3. And now we just plug in that value finally. So 9 times 1/3 is 3, plus 3 is 6. So the velocity is 6, and that's going to be meters per second. Well, probably. We didn't actually say we'll say units per second, because we don't actually know that it's in meters, because that wasn't part of, why won't it erase? Okay. Units per second. And if we were looking for our acceleration, that'd be units per second squared, like that. And position is obviously just in linear units. Okay, not too many questions left now. Just a few. Oh, it does not like to work with me. Okay, so for number 9, we need to determine which of these limits exist and figure out what they exist as, if they exist at all. So for the first one, we're approaching x equals, we're looking at the limit of this function as x approaches 3 from the right side, right? So values larger than 3. And if we think about that, if we plug in our 3 down here, we're obviously going to get a 0. And we'll get a 0 on top. And we don't want that. And there's no reason that anything would be out of our domain per se. So it looks like this should have a limit. Because from the right side, it should not exist. It might be infinity or negative infinity, but there should be some limit there. So what we're going to do is from the right side, we know that we're going to be looking at positive values, and let's plug in a positive value just to test this out. Let's say I plug in 4. We're looking at values, not positive values, values larger than 3. So let's plug in a 4, and that's going to be a negative 12 there, so it's going to be 9 minus 12 equals negative 3, absolute value of 3. So that tells us that this is going to be, if we want to get rid of this absolute value, it's going to be a negative outside of there, right? Because if we plug in that 4 now, without our absolute value, we're going to get 9 minus 12 equals negative 3, but because there's this negative outside, it becomes that positive 3 that it needs to be. So, and I'm going to distribute that negative, so it's going to be a negative 9 plus 3x. And it's still over our 9x squared minus 27x, and so now we want to see, like usual, if we can factor anything out. So I'm going to move these around just so that my x comes first. Oh my goodness. What? Okay. So it's going to be 3x minus 9 on the top. I'm going to try factoring out a 3 from the bottom. Nope, I'm going to factor out a 3x. Sorry. Because I think that might help. Because that'll be a 3x minus 9. Bada bing, bada boom. We can just cancel those out. It's 1 over 3x. So this approaches 1 over 9 if we plug that 3 in. We want to do the same thing over here, except it's approaching from the left. So we're going to get values less than 3, which means that when we plug them in here, it's always going to be positive even without the absolute value. So we don't have to alter it in any way. It's just going to be 9 minus 3x over 9x squared minus 27x. Again, we like to factor. So we'll factor out the same thing because we saw that kind of worked. we factor out that 3x, we get 3x minus 9, and that doesn't quite cancel out, so we need to factor out a negative from either the top or the bottom. I'll just do it from the top. So it's going to be, oh, sorry, I put an x there where there isn't one. That should just be 9 there. So it should be negative 9 plus 3x, and now, obviously these are written differently right now, but they are the same thing because I can just move those around. So now I get negative 1 over 3x. So the limit from the left approaches negative 1/9. And because this is the same function in there, we can just look at our right-handed and our left-handed limit and see that unfortunately, while they're pretty similar, they are not the same. And because they are not the same, our two-sided limit does not exist. So these are our answers. Okay, now for negative number 10, sorry. So it tells us that this function g of x is differentiable at x equals -2. They give us the equation for the tangent line of g of x at x equals -2, and that is this. It's 14x plus 2y equals 6. So we want to find g of -2 and g prime of -2. And all that this means is that we want to figure out what our y value is at x equals -2, and we want to figure out what the slope of the original equation is at x equals -2, which is pretty easy since this is our tangent line equation, right? 14x plus 2y equals 6. We know that the slope in this equation is going to be whatever g prime of -2 is. So let's put this in terms of y, make it easier on ourselves. It's going to be like this, then y equals -7x plus 3, and our slope is -7, so that tells us that g prime of -2 is -7. Now, we know that that is what it is at -2, so we need to figure out what our y value is at that point, which means that we're going to just plug in that x value of -2 and see that that gets us y equals 17. And this is because, like, when we found our equation for a tangent line earlier for a different function, remember we used the same x and y values when we plugged that back in to figure out our b for our slope-intercept. So the x and y values of the tangent line equation are going to be the same as the x and y values at a given point, if you're given either the x or the y. So g of -2 is 17. Okay. Now, this one is a little bit of trial and error. It's a little bit tricky to do without just trying some values. So we want to find an integer n, so the interval in the form of n to n plus 2 contains a solution to this equation. So the equation is x plus 2 plus 3 over x equals 2, so I'm just going to move that over because we're looking for our zeros. So we're going to be looking at this function here. And we notice right off the bat that x cannot equal 0, right? Because that would have an x in the denominator of part of our function, which would make the entire thing undefined. So we don't want any intervals that have x equals 0, because we can't guarantee that there will be a solution on that interval. So instead, let's just try plugging in some numbers. I'm going to try plugging in, let's try plugging in a -1. So if I plug in a -1, let's give me a 1 plus 3 over -1, which is -3 minus 2 equals -4. Okay, this was when I plugged in a -1, so I'm just going to write that there. And obviously we can't include 0, so let's try going back from that, because we see that's an n plus 2. Let's go down to -3 and see what that gets us. So -3 is going to be 9 plus 3 over -3 is a -1 minus 2 is a +6. So lucky us, it looks like this interval works. And because we've got a negative value and a positive value on it, which means that there has to be a solution on that interval if the function is continuous on that interval, which it is. And that is by the intermediate value theorem. And so we're going to say that n equals -3, because that would be our n, and then n plus 2 is 1. And we just found that f of n is a -4, and f of n plus 2, oh, no, we did not. We found f of n, which is our -3, is 6, and f of n plus 2 is -4. And now we want to know what intervals our function is continuous on. Well, the only thing that would cause any discontinuities is this bit where we've got that x in the denominator. And all that means is that x can't equal 0, like we addressed earlier, which means that it's continuous on every x value except for 0. So the function is continuous from -infinity up to 0, not including 0 obviously, and 0 up to infinity, which means that since this function is continuous on the interval provided, because it doesn't include 0, we know that there must be a solution by the intermediate value theorem. All right, and now we are in our home stretch. Just got 3 more problems to do, and they're all pretty similar. So let's go ahead and look at number 12. So we want to find the limit of this function as x approaches 12 from the left. I don't know why it does that. So as x approaches 12 from the left, which means we're going to be looking at values less than 12, right? So thinking about that, if I'm plugging in values less than 12, getting closer and closer to 12. Oh my goodness. That's going to be within my domain, right? Because if I have 12 minus 11, that's the square root of 1. If I've got 12 minus 10, that's going to be the square root of 2 in here. And those all work. It's only if we get values larger than 12 that we're going to be outside of our domain here. So this limit does exist. And if we plug in those values, we can kind of see that as we get closer and closer to 12, this denominator is going to get bigger and bigger. No, sorry, smaller and smaller, right? Because if I plug in, say, 6, right, it's going to be the square root of 12 minus 6, which is the square root of 6. And then if I plug in maybe an 8, as we get closer to our 12, that's going to be 12 minus 8, which is the square root of 4, right? Then I plug in a 10, like we said earlier. Oops. Which is 12 minus 10, that's the square root of 2. So it's getting smaller and smaller, which means that our function overall, since that's in our denominator, is going to be getting bigger and bigger, somewhat exponentially, but not exactly. Which means that this limit actually approaches, oh, that's the eraser still, sorry. This approaches infinity. Now doing number 13, it looks like the exact same thing, except now our function is a -2 on top, and we've got an 8 to go in. We're still looking at values less than 8, so we're within our domain, all the same. If it was, say, an x minus 8, then we would want to be looking at it from the right side. Otherwise, we'd be out of our domain in that radical. But it's not, so we are in our domain for all of this. And in this case, the exact same thing's going to be happening, right? As we get closer and closer to an x value of 8 from the left, our denominator gets smaller and smaller, which means we're dividing by less and less, which means our overall number gets, in terms of absolute value, bigger and bigger. But in this case, it's getting bigger and bigger in the negative direction. So this one's going to approach negative infinity. And then number 14 is a really similar problem, except now we're approaching a 13 from the right, which means we'd be looking at values greater than 13, which if we try that, any value that we plug in that's going to be greater than 13 is going to get, is going to be undefined, right? Because if I plug in even like a 13 and a half, right, it's going to be 13 minus 13 and a half, which is still a negative in our radical, which is undefined. So I clicked the eraser. Oh my goodness. Which means that this overall does not exist. It is undefined for all values approaching 13, except for 13, obviously, because that would be a 0 in there. Oh, no, including, because it's in the denominator. And that was the last one. So I think we covered quite a bit in this one, and I really hope that my explanations for all of this made sense, or at least a little bit of sense. And yeah, this video is all done. Once again, I hope that this was helpful.